Okay, welcome everybody. So I'm Jelle. I work at Red Hat. I'm also an Arch Linux developer, and I'm also involved in the reproducible builds project. So today I'm gonna introduce Cockpit for everybody. Well, maybe first, who knows Cockpit already? Has ever used it? So it's like 5 people, yeah. So I'll give a small introduction. What we want to, so why do we want to test Cockpit, and how test, so how our testing infrastructure looks like, and yeah, that's it. So Cockpit is basically someone in my team calls it GNOME settings in your web browser. So it's basically a UI, a web-based front end, which you can use to see everything on your server. So I have like my demo here. So in the general overview, you can see your software updates. You can see systemd services. There are metrics you can look at, and performance information. And this is all on your live system. So we also have a terminal. So you can see I'm running on one container. I can stop this container. We have no separate completion. And if I look at our GUI, nothing is running. If I start something here, what do we want to start? I see it's running. I look at my server. It's running here as well. So everything is basically what you normally would do with SSH. You can also do in Cockpit. It's just it is mostly aimed for like Windows administrators, but also normal Linux administrators who want to quickly see a visual view of their server. So this is everything you can manage with. You can format disks, you can configure looks, RAID, firewalling, network, etc., etc. And then there's troubleshooting. So there you can see, if you're running RHEL, for example, or Fedora, you can see your SE Linux issues, and you can fix them. And I think we also have an option to generate an Ansible playbook, and then you can apply them on all your other servers. We have plugins. So there's a plugin system. It's fairly easy. And two of the most prominent plugins we have is the Cockpit machines. So this is a libvirt front end. You can manage your virtual machines. You can do migration between two libvirt domains, and you can basically do everything a normal user would like to do. So with virtual machines. The same with Podman containers. So you can create containers, manage them, interact with them. Cockpit itself is there's a C part, and there's the front end is JavaScript. We use React. We have React UI framework, and Cockpit authenticates with PAM. So if you log into Cockpit, you log in with your normal username and passwords, basically. So the architecture looks like there's the Cockpit web server. This handles HTTP. This serves the HTML, JavaScript assets, and it talks to the Cockpit bridge. And the Cockpit bridge Podman to libvirt to almost anything which has a dbus API on your server, and this can be on your local machine, but it can also be over SSH to a remote machine. And we can also call from the UI, we can also run shell scripts. And so Cockpit supports quite a lot of the distributions. It supports Fedora, RHEL, CentOS, Debian, Ubuntu, Arch Linux, Clear Linux, and Tumbleweed. And now we roll into testing. So as you can see, we have we have quite a lot of distributions to support, and we have some goals we want to achieve when testing. So when somebody introduces a change or a bug fix, we want to run those tests on everything we support. If we update, for example, our dependencies, so this would be Fly or React or some JavaScript library we use, we want to run our tests. And if a distribution updates its packages, we also want to test that. We want to see if there are any regressions or issues in Cockpit. So those are our. So to run our tests, we need a test environment, and we want to have some. We have some things we need to we want for this test environment. So we ideally want to be isolated. So we don't want the packages on the system we test to change. We also want to some functionality we have. So, for example, setting up crypto policy. So to configure FIPS, for example, we need to be able to reboot. And we want to be so run test once. It should be have some tests which require a third-party service, like a server, or FreeIPA, or our subscription manager. So we also need to be able to talk to a different machine. So our solution for this is to run tests, to have a virtual machine which we can test. And we open 2 ports with port forwarding to this. So we want to have access to the Cockpit, Cockpit itself, and we want to have access to SSH. So we can inspect the machine, we can run commands on the machine, we can upload things to the machine for testing. And we also need to sometimes talk to external service, and for that we use libvirt, so we have like a shared network between our 2 VMs, and they can talk to each other. So now the question is, like, how do we make such a VM so we can test on it? So for this we have a Python script which usually fetches a cloud variant of the distribution we want to test. So for example, Fedora has a cloud QCOW image. We pull this, and then we run. We start it with a cloud init ISO. We create it, and we set up we configure our users, so username and password, and set up SSH keys. And from then on, we have full control over the machine. So we can run we basically run then a bash script. This installs the packages we need to test, because we want to test offline, so we don't have any external like things calling back and changing the machine or fetching updates in the background. We save this image as a QCOW, and then we upload it to our S3. So this is basically how you do this. I do this on my laptop. I run this image create script. I give it a distribution we support, and in the end we get a QCOW image. So now something we can test against. And we also we automated this whole process. So we have a GitHub workflow which runs every night. It then checks if our image is out of date, and out of date means if it's older than 7 days. We then open an issue in GitHub saying like this image has to be refreshed, and then our CI picks up this issue. It creates an image. If it's successfully run, it uploaded the image to S3. So for in the future, when we run the test, we can fetch the image from S3 and run the tests. We run the test. I'll get into that later. And if then everything is successful, so this also opens a pull request. And if everything is successful, there's a pull request. And you can see that the tests have completed, and you can merge this. And then we have an updated image. Now, and now we need somewhere to run this test in CI. And we do this in a container, because that's an easy, fixed way, and it should be reproducible to run it. So we have we create a container image with like libvirt and all our testing dependencies, so a web browser, and then we also need when we have this container to run the test in. We do need dev KVM access. That's a bit tricky, usually, if you want to run it somewhere in OpenShift. And we also want to test against multiple browsers. So what we use in production is like we have a bare metal CI, which is basically a machine we can provision ourselves. And we run Fedora IoT on this, and then just spawn task containers, which pick up the jobs. We also run them, have some OpenStack environment we can use, and if both environments fail, we can fall back to AWS. So you can see if you run your test in a container image, it's quite flexible to where you can run it. And so this is basically this diagram describes the workflow. So how we run our test. So when somebody opens a pull request, we send GitHub sends a webhook, initiates a webhook, and sends what pull request it needs to test to our a Podman container we have, which runs the webhook, and it puts these tasks in a queue, and it's a RabbitMQ. And the workers then periodically, when they're not working, they look at the queue, they pick a task to work on, and they execute the tasks, and then report back to GitHub. So I can, and so that's how we run our tests. And now I'm going to discuss how our test framework looks like. So we have a web application to test, but we also need to be able to inspect the system state. So for some of the tests, we modify, for example, we stop a container, and then we have to test if it's check in the browser if it's actually stopped. So so that requires some more functionality than your normal web framework, test framework. So we started back in the days before I joined. We used Phantom.js, and that got deprecated at some point, and then the team discussed like where do we move next, and we looked at the several alternatives, but most of them require like download a browser for you or do some things we don't want, or are written in JavaScript, and our tests were in Phantom.js were written in Python. So we decided to write our own test framework, basically. So we use the Chrome debugging protocol with a small Node.js module. So this is Chrome interface. And you can basically control the whole browser with this. So you can resize it, you can execute all the jobs. This is good enough for us. And we want SSH access into the machine. So yeah. Let me demonstrate how this works. So this is running one test. Is it readable, by the way? Or should I enlarge my firmware? So the TestOS environment variable tells us like which image I want to test against. So this is Fedora 35. Then I set the this environment variable controls if I want to basically run in a headless mode or not. So in this case, we're not using headless mode. We're going to show the browser. And then we call the tests class, and this is the test we want to run. And the cool thing about our test framework is that it also has the option to sit in the test. So when I spawn the test, what? Oh, demo effect. So now we start our test image, and this takes a while. We do some setup. We log in. And now the execution stops. So this is because it's a bit spammy. So this is the test we are running. So let me see. So all the way to the top. So the first thing we did is do some cleanup, because this test can. This is a non-destructive test, so we can run this basically anytime, every time if I spawn, I can. So this way I'm running the test. It always spawns up a VM, but there's also an option to pass an SSH port and a web browser port, and it will reuse an already running VM. And for this, for the non-destructive test, it basically means that they clean up after they're done. So if I run this test again against already running VM, it succeeds. It doesn't modify any modifications it makes during the test. They are restored after it's done. So the first line was log in and go. So we log in and we reach the overview page. And now there's a sit. And the sit is basically, it stops executing and waits for me to press enter to continue. So this is a useful way to debug our tests. So now I press enter, and it executed the following line. So it changed MOTD, and you can see this is the MOTD is also shown in Cockpit. And then I can press enter again, etc., etc., etc. So this is how the tests are run locally on a developer machine. So what you just saw was basically this process. So we spawn the test machine, we launch the browser, our test script talks to the Chrome Developer Protocol driver to basically tell where it has to go, tell what JavaScript has to execute. And we use SSH to, for example, run the printf command. So this is executed on the host itself over SSH. Yeah, so this is basically this example. What we also do in our tests is we look at the journal, and if there are any messages in the journal which we don't expect, error messages, then the test will fail. So sometimes we have to allow messages to be. So this is basically this is how we see if there are like any SA Linux policy violations or any other errors which happens during testing, which you want to catch and then report upstream. So sometimes we have to allow things which are just error messages, or which happen because we kill the service or something. So we have to allow those. We also can't really run all tests on all distributions. So we skip tests on, for example, this one is because Network Manager Ubuntu lacks some, so we have to keep it, and this is done with a Python decorator. And then there's these non-destructive tests, which I also already explained. So these basically, if you do them, they clean up after themselves, and the next time, and they shouldn't interfere with other tests, which are run afterwards. And we've done this because if you run a test and then reboot the machine to get a clean state, it takes like a very long time to run your tests. So our tests now take like 40, 50 minutes to run. If you would if you would reboot for every test case, it would be like 3 minutes per test extra. So that's not very nice when you're developing. But before you can actually run these tests, we have this. So we created this image, but this image doesn't have the subject yet which run the tests. So for this, we need to prepare the image. So image our CI creates, and we run the script. And the script builds a Cockpit package in the machine. So we first we spawned the VM. We built the package in the VM because we support multiple distributions, so we cannot always build it on the host itself. So we built a target VM, and the installed package, or the package which comes out of it, we install in the VM, in the spawned VM, and we can also run some setup scripts. So, for example, we might want to auto start Podman. If we want to test Podman, then we can run this as a prepare step. And this image then is saved locally. Then if you execute CentOS Fedora 35, it won't pick the raw image, it will pick the prepared image. Yeah. And in CI, we actually use a different entry point to run the tests, because in the CI we are more critical of our tests. So if a test fails in CI, we don't automatically fail. We retry it 3 times, and if it failed 3 times, then we fail the test. So this is because some tests can be flaky, and it's always something you want to circumvent. But it's nice if you can at least retry it once, because if one test fails out of your 60 tests because it's flaky, that's really annoying developer workflow. Also, if you introduce or change the test, we automatically run this test 3 times in a row to make sure it isn't flaky. And in this case, if one of the 3 attempts fails, we do fail the test. So we don't introduce any flaky tests, which depending on some timing, fail. So this is, for example, this does happen sometimes. So when I write a test on my own machine, it is slow to execute than on our bare metal CI, which runs like 10 times faster. So this is a good way to not introduce any flaky tests. And we have this concept of naughties, which I'll explain later. So these are all, every time you run in CI, these are tracked. So I'll take this next slide. So this is for an example of a pull request. I can also open, I have one open, I think. It's maybe a nicer. Yeah, this one. So these are all also here. Yeah. And yeah, this is what I want to talk about. So we also made a custom logging thing for the output of our tests, and this is actually pretty cool. So this is a web page. You can see that all the tests which failed. The green tests are the tests which succeeded, and the yellow tests is the tests are skipped. So they're either skipped because there's a known issue. So this shows there's a known issue. So we're skipping this test. And it can also skip because this distribution doesn't support this feature. And this is, yeah. For example, so this is a failing test. what you get here is the normal test output. And we also save the journal. So for example, if there's like a segfaulting service, you can look in the journal. Oh, this daemon segfaulted, then probably this is why my test failed. Also, alternative, you also have a screenshot. We take a screenshot if the test fails, and then you can visually see that something is missing. Well, not sure why this test fails, but sometimes it is useful to have a screenshot. And developers can also trigger this test manually. So with a small shell command. So if something fails and they think it's flaky, they can just retry it. But it's also or they can also run tests against an image, which is not in the default test set. So, and I'll explain the naughties. So the naughties are a way of how we keep track of downstream issues. For example, we built or a 36 image, and we test it, and something in libvirt is broken. Then we investigate, and we find out, oh, this is a bug, or either it's a bug or it's like we have to use the API different. This is basically the two things which can, or the test is flaky, but so if it is a bug, we report a bug upstream or downstream, and we create a GitHub issue. And we reference then the bug report, and we make a file. And in this file, we put the backtrace of the failing tests, and this file is then put in our bots repository, and then this test is automatically skipped. So, and every time the test runs in CI, it will run the test, and if it fails, it's like, oh, but I know this is a known issue, so I'll skip it. And if it succeeds, it will not. So if it fails, it will update the issue. You open a GitHub with like, this is the last. I can actually have this. Show this. So if it fails, it will update the issue with like the last time it failed. And if it succeeds, it doesn't. So let me. Notes. Yeah. So here it is. So this is the issue, and then the bug reports, and then our CI ran on Fedora CoreOS. The test failed, and then it updates this the comment, and you can see every time it fails. So it keeps the 10 latest comments, so we don't get an endless. What is it? So we don't endlessly spam the GitHub issue. So and if this doesn't occur. If the test succeeds and the last comment wasn't updated for 21 days, then we make a PR to remove this naughty. And so So the naughty looks like this. So you can use regex to like remove some. Well, as a Linux policy violation, for example, the PID is in there. It always changes. And so when this no longer fails, we create a new PR to remove this file, run. And if the test succeeds, then you can remove the naughty. So it's automatically cleaned up. And then we also inform we check the bug report we made was closed or not. And if it wasn't closed, then we report like, hey, we didn't see this issue anymore. Maybe we want to close it. Another cool thing about our test CI is that we have one of our external dependencies is a UI framework, which can, with updates, have regressions, and we could visually inspect, like we could update the node modules and then check it out locally and check if everything is okay, but it's like too much work. So my colleague wrote wrote pixel tests, and this is a part of our test suite. So this is in the test code, you can say take a screenshot, and when the test then runs in CI, it this existing screenshot we have. We store this in the Git submodule, and it compares it to the current screenshot. And if it changes, the test fails. So this is a nice way to how we catch regressions from our UI framework, or if somebody changes something in the GUI, which has or in our CSS, which has unintended changes, we fail the test. And this happens on multiple versions. So we have one test case for the desktop and one for mobile. We also have some coverage because we use the Chrome developer, the debug protocol, and this gives us access to the Chrome's native, what is it? They have like a coverage tab in developer tools, and you can also read this with the debug protocol. So all our new this is fairly recent, and our new PRs also put in comments like when something is not covered by a test. And so what I just talked about was everything, the infrastructure we maintain ourselves to test things on multiple distributions. But Fedora also offers a system to test packages in CI, and it's pretty cool. So basically you define a YAML file in your project, and you say which Fedora versions you want to test, and you give it like the packages you need to install, to have installed for your tests, and then you give it entry point. So this can be like a shell script which runs the tests. And we also use this. So this is something you, for example, saw in this PR. So this is the testing farm. And basically it uses Fedora's existing build infrastructure, so Copper, to build the package from pull request. And then it gives this package to the testing farm, and it installs the package. So you get like one small VM with, I think, 1 GB of RAM and 20 gigs of disk space, and you can run your tests in there. So for us, this means we cannot reboot, because rebooting would reboot the test VM we're testing in. So we can only run a subset of our tests in there, which are non-destructive, so they don't affect the host. Everything we test, every test run we also store in a database, and we export this to Prometheus. So we store the test sets we run. So for example, Fedora, how many tests we ran, how many were skipped, and then we have a separate table which records individual tests with the test name, if it was retried, and how long it ran. This SQLite database, we basically get some metrics from there, and for that we have a Grafana dashboard, of course. And so I looked it up, how many tests do we actually run every month, and it turns out we run about 2 million tests every month on all our distributions we support, and all the so this is for Cockpit machines, Cockpit, Popman, and 3 other plugins. And in this dashboard, we also track like how often a test failed. So if a test fails like 60% of the time, then it's probably something we use to investigate and see if there's some flaky behavior you can fix. There's also this. So what I just talked about also comes into something we have defined is the error budget. So this is basically an SRE site reliability engineering concept. So it's more for running services. but we also applied it to tests. So basically you say, if X% of my tests fail randomly, we basically get we don't have an automatic alert, but the graph becomes red. Or if it takes too long, or if the the test queue, so the test suits we need to run, the queue length of it is higher than something we expect, then this is something we should fix. So we had this once this year, so the test took too longer than the allocated time we thought for it to run. And we did some restructuring of how we run our tests to resolve this issue, or to take a look at like what is the longest. Why does this test sweeps, which does something with Drake, it takes so long? Well, it turns out we have 3 kernels installed, and then Drake has to regenerate the init manifest for every machine 3 times. So we removed so this is something we do to basically keep ourselves happy, so that the CI doesn't take too long, that the tests don't fail too often randomly. Yeah, that was it. So I also looked up like how many bugs did we actually find in FAL for the distribution. So for Debian it was only 3 this year, from what I can roughly find. And for Fedora, RHEL, and CentOS, we had like we reported 20 bugs in the last 3 months. And then there's other fun stuff we have. So these are the top offenders of the things which fail often in which make our tests, our image refresh. So when we build a new image and we run the tests, these are the top offenders. So SE Linux is of course number 1, and libvirt also. Yeah, and what we would like, so because of this slide, so we would like to. So what happens now is we pull in a new Fedora 36 every 7 days, and we run our tests. And then we find out something is broken. And that's a bit annoying. You would rather like fix the problem up front. So if somebody releases a new thing which Cockpit requires, we will rather have them maybe run our tests. So this is what we call reverse dependency testing. And this is sadly not applied yet. So this is something we would really like to have in the future. So for example, a new libvirt comes out, they build it, and the Fedora CI runs the Cockpit tests with such libvirt, and then if they fail, then can investigate like, oh, maybe we need to fix something or hold back the package, so we don't have to after the fact report an issue. And yeah, are there any questions?